We've seen the interpretation of the derivative as a rate of change, and we're going to extend on that a little bit here and look at what are called related rates. It turns out we can take our derivative to relate different quantities by their rates, which means we have related rates. And so these are the types of problems you see. Here we've got an oil rig that's out in an ocean or a sea, and it springs a leak, and once it does, you start getting these concentric circles, or this circle that's expanding and expanding in an oil spill. Now, it's a little bit idealized because certainly there's currents and whatever, and it wouldn't be necessarily a perfect circle, but we'll just sort of get an idea of how you might try to measure how fast this oil spill is spreading. And that's what it says here. So you've got this patch increasing at a rate of 30 meters per hour, the radius is, and we want to know how fast the area of that oil patch is increasing at the point when it's got a radius of 100 meters across. So that's our question. So it sounds a little complicated. How do you figure that stuff out? Well, we can see some rates in here. So this is how I know it's a related rate problem. It tells me, you can see these rates given, meters per hour. That's a rate. And we're told we want to know how fast the area is increasing. Well, that's another rate. Fast is velocity. And then this is not a rate because it just says 100 meters. So how do we draw out the information that we need and work on a problem like this? Well, let me give you some steps here that sort of help in these problems, and we'll go through these for this one. Let me give myself a little more room here. So the first thing it says when you're looking at a related rate problem is kind of one of the things I've already done. It says determine the givens and the unknowns. That is, determine the knowns and the unknowns. Draw a picture if it's useful. I've kind of got a picture here. It's not that useful. This is a circle that's getting bigger. It's got a radius. But this is something that can vary, so you go ahead and label it R. Don't put the 100. 100 is a particular value of R, but this is a changing quantity. This is a circle that's getting bigger and bigger. There's really nothing else to label on this circle, but I know what I'm trying to find. I'm looking at this biggest circle, say, and I'm trying to find how that area is changing as the R changes. So that's first thing. Determine the knowns and unknowns. Well, in this problem, let's start with the unknown. It's usually, you go straight to the question. This question says, how fast is the area of the patch increasing? So I want to know something about how the area is changing. And that's what the derivative gives us. So I'm just going to say, I want to know dA dt. What is the derivative of the area with respect to time? Because that's what's happening. We've got area changing with respect to time measured in hours. So when you're doing a related rate problem, your knowns and unknowns can be derivatives. You just have to figure out which ones are derivatives and which ones aren't. Well, so that's the only unknown at this point. And then the second question is going to be asking for the circumference, but we'll do that in a second. The knowns, usually you can go to the numbers. I got a 30 and 100. The 30 is the rate of change of the radius. So it says if the radius is increasing at 30 meters per hour, so I'm going to say I'm given dr dt, that's the change in the radius, is 30 meters per hour. And I'm given this 100 meters, and that's a specific value of the radius. So I'm sort of this thing is increasing, and then I'm going to take a snapshot at 100 when R is 100. That's why I don't put 100 here yet, because this is a dynamic figure. It's moving as I go through. And so the other known, I'm going to put it here just so I don't. 100 meters. So there's my step one. I drew a picture. Don't really need it in this problem other than to kind of keep my bearings straight, not to put the 100 in place of the R. The R is changing. But I've got my unknown. That's what I'm trying to figure out, solve for, and then my knowns. Okay, second, now you get a formula that relates the dependent variables. Dependent meaning dependent on time in this problem, because time is the thing that's independent. It's just moving forward. So we want to find a formula that relates these independent variables, A and R. They're both functions of time. And so in this problem, it's a known formula. So it says use the picture if you need to, look for triangles, whatever. In this case, it's just a known problem. We know that the area of circles are given by pi r squared. That's the relationship between the variables. What we're looking to do is relate the rates now. And that's what step 3 lets me do. Once I've got a formula that relates the variables, even though these are both functions of time, I could have put them in as a of t equals pi r of t squared. That's technically what I have, because they're both changing with respect to time. And so now when I differentiate this, I have to use implicit differentiation because the actual variable here is t. And so on step 3, I take the derivative of a with respect to t. This is really, like I said, a of t equals pi, the derivative of this side. So I'm using implicit differentiation, differentiate both sides. And on this side, well, I take the derivative with respect to the variable I see, which the derivative of a with respect to a is 1. I just get dA dt. I mean, there's really no reason to go through the chain rule on that one. You just get dA dt. On this side, pi is a constant. The derivative of r squared with respect to t, I take the derivative of r squared with respect to the variable I see, which is r. So it's the derivative of r squared, 2r, times dr dt. And so we've managed to use implicit differentiation now to give me a formula that relates the rates. And that's where the title of this section comes from. It's related rates. This tells me how the area is changing based on how the radius and how the radius is changing. And so that's what step 4 tells me to do. I now plug everything in all my knowns, hope that I have enough to figure out the unknown. If not, sometimes you have to go back to your picture. Sometimes you go back to your formula. In this problem, I've got everything I know. Everything I need. I've got r. That's one thing I need to figure out dA dt. Well, there it is. That's where I'm now going to say at that particular r, I want to know the answer to this. And I've got a particular rate. This is not this is constant rate all the way throughout. The radius is changing at a constant rate. And so what I've got then is that dA dt in this problem is going to equal 2 pi times my radius, which is 100 meters, times dr dt, which is 30 meters per hour. And if you work this out, you're going to get 600 pi square meters per hour. And 600 pi, if you get to get a calculator, this is approximately 1,885 square meters per hour. In other words, the units are right. If your units had come out to be just meters per hour, that wouldn't make sense because area is measured in square meters. So you need to make sure your units turn out. If your units aren't turning out, that means you've got a problem with your dimensions in the problem. You've got the wrong equation somewhere because the dimensions have to match up properly. What I say is my final dimension needs to be the dimension of the thing I'm claiming. So here's a quick picture of what's going on. So this little red dot in the middle, that's where the leak has sprung. And so I'll just put this in motion. And you can see I've got just this little ticker down here that's keeping track of how fast the radius is changing. You can see that area is speeding up a lot faster. And that's what's happening. It's going at a rate over here of 1885 square meters. It's adding on area a lot faster because that radius, as it's pushing out, it's pushing out a kind of a disk of area as it goes, and that disk of area gets bigger and bigger because it's farther and farther from the center of that circle. So as this thing grows, you can just see that area pushing out very quickly. Now, so this isn't that realistic because usually the oil spills out at a constant rate, which means that it's actually the area that's probably building at a constant rate, and the radius then would be slowing down. It starts out quickly, but as it starts to build, you get more and more area. But anyways, so we kind of have it the opposite here, but it gives you the idea of how to work it. And then all I have to do now to do the circumference is the unknown. Instead of being dA dt, it's going to be dC dt. Everything else is still the same. How fast is the circumference changing? So I'm going to leave my knowns there. My formula that relates to 2 now is the circumference is 2 pi r, pi times diameter. And so now my related rate equation, taking the implicit differentiation of both sides, well, that's just going to be 2 pi dr dt. And so I don't even need r. This is actually saying that my circumference changes just like a multiple of my radius. In other words, it's proportional to my radius. And so what I get in this case is the circumference is changing is 2 pi 30 meters per hour. And if you work that out, that gives you 60 meters per hour. So the circumference is changing at 60 pi meters per hour. And if you use a calculator here, you get about 188.5 meters per hour. And these units make sense because circumference is a linear quantity. It's a distance around, and so distances are measured in meters. So that's the right measurements, that's the right units. But it says it's a linear thing. So as it is faster, because as you push that radius out, it is, you have to put more length around that outside to keep up with that radius, but it is linear. It's nice and proportional. It's not squared like up here. So it does grow sort of at the same rate as the radius. It's just a different number for that rate. All right, so that's a quick overview of how we do related rates. We'll look at several more problems to kind of get the idea of how to use the different parts of these steps that you were given.